Number 12, what value of x will make this a probability vector? Well, all we need for a probability vector is numbers that are in between 0 and 1, and these numbers have to add up to 1. And so really, just do this in your head, it's going to have to equal 0.2. That's it. 13, draw a transition diagram. So we're looking at states 1 and 2, going to states 1 and 2. And so we have two states. I have a state 1 and I have a state 2. And we're talking about the probabilities of traveling in between and back and forth. From state 1 to state 1, from state 1 to itself is 0.2. From state 1 to state 2 is 0.8. From state 2 back to state 1 is 0.9. And from state 2 to itself is 0.1. That's transition diagram. Now 14 says go the other way, take this diagram and make it into a transition matrix. So we can see three states. These states are A, B, and C. I think it's helpful to label them. And we're just looking at the probabilities of going between the states. State A does not go back to itself, so state A to state A is 0. State A to state B is 0.2. State A to state C is this 0.8 right here. State B to state A is 0.4. B to itself, nope, that's 0. B to C is 0.6. Notice the rows all add up to 1. That has to happen because we're talking about probability. C to A is 0.1. C to B is 0.9. And C to itself is 0. There's your transition matrix right there. 15. Markov chain has the transition matrix of that. Find the probability that an object which starts in state 1 will be in state 2 after 4 transitions. So if I'm going from state 1 to state 2, I'm talking about this position, but that's only one transition in the transition matrix. I want to go from state 1 to state 2 in 4 transitions. So what I need to do is I need to take this transition matrix to the 4th. I'm going to take p to the 4th power. And I'm going to use a graphing calculator to do that. So let's go to matrixcalc.org. Matrixcalc.org right here. I'm going to clear that. Whoops, I'm going to clear that. And it was a 2x2, 0.4, 0.6, 0.8, 0.2. I'm going to take it to the 4th power, raised to the 4th power. And so here is the 4th power of my transition. Okay, that's p to the 4th. That's my transition raised to the 4th power. So again, if I'm going from state 1 to state 2, I'm looking right here. The answer is 0.4176. Find the equilibrium vector for the following transition matrix. Okay, well the easiest way to do it, again, the easiest way to do it is to use a calculator. And so that's just what I'm going to do. It is a 3x3. And where are we? Number 16 is 0.1, 0.1, 0.8, 0.4, 0.3, 0.3, 0.1, 0.2, 0.7. Equilibrium vector is talking about long term. I think the easiest way to do this is just pick a really high power. We'll pick like the 99th power, and we're basically going to take this and take it to the 99th power. Any large number will pretty much work. You're looking for these numbers to match. A lot of times they will. Sometimes they won't. You'll have to kind of figure out what that means, interpret the results. But when they match, it's useful information because we can tell that it will always end up in state 1 it will end up in state 1 with probability 0.1613. That's what that means. I'm going to try it to 8 decimals and see that it really does match. Yeah, these numbers are matching out to 8 decimals, so that's a pretty good result. It's not exact. It would be better with fractions. A fractional answer would probably be a better answer, but I'm going to do this just kind of a quick rundown. So what this means is whether you start in state 1 or 2 or 3, the probability of ending in state 1 is 0.1613. I'll round up to 4. And whether you start in 1, 2, or 3, the probability of ending in state 2 is 0.2043. And whether you start in state 1, 2, or 3, the probability of ending in 3 is 0.6344. And so I like to display the result as a vector. A lot of times that's called the equilibrium vector right there. And that vector shows the probability of ending up in state 1, 2, or 3.